here is something nobody tells you. The planet you are lying on right now has been here for 4.5 billion years. Before oceans, before oxygen, before anything alive ever drew a single breath. This world was already ancient, and in all of that time, all 4.5 billion years of volcanoes and ice ages and mass extinctions, humans have existed for less than 0.07% of it. We are not the story of this planet. We are the last sentence of the last paragraph. So when scientists sit down and quietly ask the question, how long might humanity actually have left? The answer they find is not what most people expect. And tonight, we are going to follow that answer. Slowly. All the way back to the very beginning of this world, and then forward. Further forward than most people ever allow themselves to look, because the picture that science reveals is not a warning. It is not a countdown. It is something far stranger and far more vast. But before we begin, I'm always curious, where in the world are you listening from tonight? And if you find yourself drawn to explorations like this, you're welcome to subscribe. That is how recently we arrived. Building cities, launching satellites, mapping the ocean floor, reaching out toward other worlds. In just a few thousand years, we have gone from stone tools and open fires to standing on the surface of the moon. But tonight, I want to explore a question that scientists have quietly been asking for decades. A question that sounds simple, but pulls you towards something vast and strange when you really begin to follow it. That question is this: how long might humanity actually have left on this planet? Not in a frightening way, not as a warning, but as a genuine scientific exploration of time, of scale, of what the future might actually look like across thousands, millions, and even billions of years. Because the answer is far more surprising than most people ever expect. Let us go back to where it all began. 4.5 billion years ago, there was no Earth. There was no sun. There was only a vast, slowly rotating cloud of gas and dust, drifting through a region of the galaxy that had no name, because there was no one to name it. And then, slowly, over millions of years, gravity began to pull that cloud inward. Particles attracted other particles. Dust gathered dust. Gas collapsed upon itself. And at the center of all that slow, quiet compression, a star ignited. Our sun, burning for the first time, pouring light into a darkness that had never known light before. And around it, the leftover material began to clump and spin and collide, forming the rocky seeds of what would eventually become the planets of our solar system. One of those seeds was Earth. Small at first, molten and violent and completely inhospitable, a world that no living thing could have survived. For the first several 100 million years, Earth was barely recognizable. The surface was an ocean of liquid rock. Meteorites struck constantly, raining down from a chaotic early solar system still sorting itself out. The atmosphere was thick with volcanic gases. There was no oxygen, no liquid water, no shelter, just heat and pressure and the slow work of time. And then, something extraordinary began to happen. The planet cooled. Water vapor, rising from volcanoes and carried in by comets, began to condense. Oceans formed. And somewhere in those early oceans, in some quiet, warm, chemically rich corner of a young and restless world, life began. We do not know exactly how. We may never know exactly how, but around 3.8 billion years ago, the first microscopic living things appeared on Earth. Single cells, invisible to any eye that did not yet exist, doing nothing more dramatic than surviving, and yet, that quiet beginning would eventually lead to everything. For billions of years, life remained small. Simple cells multiplying in ancient seas, no eyes, no movement, no awareness of any kind, just the slow, patient chemistry of survival. But life was learning. Over hundreds of millions of years, cells became more complex. Some learned to use sunlight as energy, releasing oxygen as a byproduct. Slowly, over an almost incomprehensible stretch of time, filling the atmosphere with the very gas that would one day make complex life possible. Then, around 540 million years ago, something shifted. Life exploded in complexity. In what scientists call the Cambrian explosion, a vast array of new life forms appeared in the oceans. Creatures with eyes, with shells, the ancestors of almost everything alive today, and from that point, life on Earth expanded into every corner of the planet, into the deep ocean, onto the land, into the air, filling billions of ecological niches, with an almost bewildering variety of forms. And through all of that, through all 540 million years of complex life, through mass extinctions and ice ages and continental shifts, through the age of fish and the age of reptiles, and the long reign of the dinosaurs, humans did not exist, not even close. Our earliest primate ancestors, the small furry mammals that survived the asteroid impact that ended the dinosaurs, those creatures appeared around 66 million years ago, and they were nothing like us. It would take tens of millions more years for that evolutionary line to slowly, gradually produce something resembling a human being, the genus Homo. Our direct ancestral group only appeared around 2.8 million years ago, and modern humans, people who looked like you and me, only emerged around 300,000 years ago. 300,000 years. In a planetary history of 4.5 billion years. That is less than 1/100% of Earth's total lifespan. We are extraordinarily new here. And human civilization? The cities, the writing, the agriculture, the entire infrastructure of organized society, around 5,000 to 6,000 years ago. Writing, less than 6,000 years ago. The Industrial Revolution, less than 300 years ago. The Internet. In the vast deep calendar of Earth's history, human civilization is so new, so breathtakingly recent, that it barely registers as a moment. And yet, in that brief flicker of time, we have reshaped the surface of the planet. We have altered the composition of the atmosphere. We have pushed species to extinction. We have lit up the darkness of the night with artificial light visible from space. In geological terms, we are a new force on this planet, so new that scientists have proposed naming our current epoch the Anthropocene, the age of humans. An age defined by our influence on Earth's systems. Now, here is where the question becomes genuinely interesting, because when scientists ask how long humanity might have left, they are not just asking about us. They are asking about the future of this planet. And they are asking on timescales that most of us are not used to thinking about, not decades, not centuries, but thousands of years, millions of years, hundreds of millions of years. And on those timescales, the picture becomes surprisingly hopeful and quietly humbling in equal measure, because the truth is, if we are careful, if we manage the risks that lie ahead, the window of time available to our species on this planet is almost incomprehensibly large. Earth itself has roughly another billion years of habitability ahead of it, before the slowly brightening sun begins to make conditions on the surface too extreme for complex life. 1 billion years. That is a number so vast that it is almost meaningless to say out loud. But tonight, we are going to try to feel its weight. But before we look forward, let us first understand the risks. Because scientists who study the long-term future of humanity do not only think about distant astronomical timescales, they also think about the nearer term, the risks that could cut humanity's story short, before we ever have the chance to reach those vast horizons. And the first category of risk is the one that perhaps feels most familiar. The risks that come from within our own world, natural planetary risks. The kind of events that have reshaped life on Earth many times before, and could do so again. The most famous of these is the asteroid impact. Around 66 million years ago, a rock roughly 10 kilometers wide, traveling at approximately 20 kilometers per second, struck what is now the Yucatan Peninsula in Mexico. The energy released was roughly 2 million times more powerful than the most powerful nuclear weapon ever detonated. The impact vaporized rock, sent shockwaves around the planet, ignited wildfires across continents, and then threw so much debris into the atmosphere that sunlight was blocked for months. What followed was a long, dark, cold period known as an impact winter. Plants died. Food chains collapsed. Around 3/4 of all species on Earth went extinct, including the non-avian dinosaurs, animals that had dominated the planet for over 160 million years. Gone, in geological terms, almost overnight. Now, could that happen again? In theory, yes. Large asteroids still exist in our solar system, and occasionally, their orbits bring them close to Earth. But here is what is quietly reassuring. Unlike the dinosaurs, we can see them coming. Humanity has developed sophisticated planetary defense programs. Astronomers around the world continuously track thousands of near-Earth objects, and in recent years, we have even demonstrated the ability to change an asteroid's orbit. In 2022, NASA's DART mission successfully altered the trajectory of a small asteroid by deliberately crashing a spacecraft into it. For the first time in history, a species on Earth had the ability to deflect a cosmic threat. The dinosaurs had no such option. We do. But asteroids are not the only natural risk scientists consider. There is another category of planetary threat, one that is slower, less dramatic in the moment, but potentially just as powerful: supervolcanoes. Most volcanoes are relatively contained. They erupt. They cause damage locally, and then they quiet down. But supervolcanoes are different. A supervolcano does not form a traditional cone-shaped mountain. Instead, it sits beneath the surface as a vast, pressurized reservoir of magma. And when it erupts, it does not simply pour lava. It explodes, releasing hundreds or even thousands of cubic kilometers of material into the atmosphere. The most famous supervolcano in the world sits beneath Yellowstone National Park in the United States. It has erupted 3 times in the past 2.1 million years. The largest of those eruptions was roughly 2,500 times more powerful than the 1980 eruption of Mount St. Helens. If an eruption of that scale happened today, it would send ash across entire continents, darken skies across the northern hemisphere, and trigger a volcanic winter lasting years. Scientists estimate that a Yellowstone-scale eruption occurs roughly once every 600,000 years, on average. The last one was approximately 640,000 years ago, which means, by the rough mathematics of geological time, another large eruption is not imminent. But it is not impossible either. What is reassuring, however, is that unlike the asteroid threat, a supervolcano eruption, while catastrophic in scale, would likely not cause total human extinction. Our species is remarkably resilient. We have survived major volcanic events before. Around 74,000 years ago, a supervolcanic eruption in what is now Indonesia, known as the Toba event, may have reduced the global human population to as few as a few thousand individuals. We were brought to the very edge, and we survived. We adapted. We rebuilt. That resilience, that extraordinary human capacity to endure, is itself a kind of answer to the question we are exploring tonight. Because so many of the risks that could threaten us have already tested us before, and we are still here. Beyond volcanic eruptions and asteroid impacts, scientists also consider a quieter, slower kind of planetary risk: climate shift. Not just the climate change happening in our lifetimes, but the deeper, longer patterns of climate that have shaped Earth across millions of years. Our planet has experienced many ice ages, long cold periods when glaciers advanced to cross continents, covering what are now green and inhabited landscapes under kilometers of ice. The most recent ice age peaked around 20,000 years ago. At that time, sea levels were roughly 120 meters lower than they are today. Land bridges existed between continents. Woolly mammoths walked across landscapes that are now beneath the sea. And early humans, small bands of hunter-gatherers, survived in harsh, cold conditions by following migrating animals and adapting their tools and shelters. We did not merely endure the ice age, we lived through it. And when the climate slowly warmed again, melting the glaciers and raising the seas, we expanded into new territories, into new landscapes, building the foundations of what would eventually become civilization. Now, here is something that feels important to sit with for a moment. Every single risk we have discussed so far, the supervolcano, the ice age, has already happened to our ancestors, and in every case, humanity survived. Not without loss, not without suffering, but survived nonetheless. We are adaptive. We are resourceful. We are quietly persistent, and yet, the modern era has introduced a new category of risk. Risks that did not exist for our ancestors. Risks that we ourselves have created. And these are, in some ways, the most sobering to consider, not because they are certain, but because they are within our control. And that means, unlike an asteroid from deep space, we cannot simply wait for the universe to decide. We are the deciding factor. The first and most significant of these self-created risks is the one most of us are already familiar with: environmental collapse, the slow degradation of the systems that make complex life possible on this planet. Earth's biosphere, the interconnected web of living things and the systems that support them, is extraordinarily complex. Forests regulate rainfall. Oceans absorb heat and carbon. Soil microbes make agriculture possible. Insects pollinate the plants that feed billions. These systems did not emerge overnight. They evolved and refined themselves over hundreds of millions of years, and they depend on each other in ways we are still only beginning to understand. The concern among many scientists is not that a single catastrophic event destroys the biosphere, but that the slow, compounding degradation of its components could gradually undermine the stability that complex civilization depends on. Species loss, soil depletion, ocean acidification, freshwater scarcity. Each of these individually is manageable, but together, over time, compounding against each other, they represent a kind of slow pressure on the foundations of human life. It is not a dramatic explosion. It is a quiet erosion. And the challenge with quiet erosions is that they are easy to ignore until the moment when they are no longer easy to ignore. And then there are the risks that feel newer still, risks that belong specifically to our era, the era of advanced technology. Nuclear weapons have existed for less than a century, and yet in that short time, humanity has built an arsenal capable of ending complex civilization. Many times over, scientists who study existential risk estimate that a full-scale nuclear exchange between major powers would not just destroy the cities directly targeted. The fires ignited by the blasts would send vast quantities of soot and smoke into the stratosphere, blocking sunlight, cooling the planet, collapsing agriculture globally. In a scenario sometimes called nuclear winter, the indirect effects, the famine, the social collapse, the breakdown of medical systems, could claim more lives than the weapons themselves. It is a sobering thing to consider that we have built something capable of interrupting our story, just as that story was beginning to accelerate towards something extraordinary. And yet, here too, there is quiet reason for measured hope. The number of nuclear weapons in the world has actually decreased significantly since the peak of the Cold War. At the height of the Cold War in the 1980s, the world's nuclear arsenals contained over 60,000 warheads. Today, that number sits closer to 12,000. Still an almost unimaginably destructive number. But the direction of travel, over decades, has been downward, and international frameworks, however imperfect, continue to place constraints on nuclear development and deployment. The risk has not disappeared, but it has, in measurable ways, been reduced. And this is the pattern that scientists who study long-term risk find. Again and again, humanity tends to recognize serious threats, and then slowly, imperfectly, often too slowly, begin to build responses to them. We are not perfect at this. We are often frustratingly slow, but we are not incapable of it. Which brings us to the most fascinating and uncertain risk of our era, a risk so new that we barely have the vocabulary to discuss it with confidence. Artificial intelligence. A technology that does not yet pose an existential threat, but which some of the world's most thoughtful scientists and engineers believe could become one, if not developed carefully. The concern is not the science fiction image of a robot uprising. It is more subtle than that, and in some ways, more difficult to address. As artificial intelligence systems become more capable, they may eventually be able to pursue goals more effectively than any human, or any human institution, can monitor or control. If those goals are not carefully aligned with human values and human well-being, the consequences could be significant, not because the system is malevolent, but because a sufficiently powerful system optimizing for the wrong objective could reshape the world in ways that are deeply harmful to human life, without any intention to do so. It is the kind of risk that is difficult to make feel real, because we are not used to thinking about systems that are smarter than us. We have always been the most capable problem solvers on the planet. The idea of creating something more capable and then struggling to ensure it remains beneficial is a genuinely new kind of challenge, one that some of the sharpest minds of our era are actively working on, with urgency and with genuine seriousness. Now, I want to pause here for a moment, because I want to be clear about something. None of these risks, the environmental degradation, the nuclear threat, the challenge of artificial intelligence, none of them represent certain futures. They represent possibilities, probabilities that scientists try to assess with the tools and data available to them, and the honest answer is that no one knows exactly how the story of humanity unfolds. No model is perfect. No prediction reaches that far with certainty. What scientists can say is that the risks are real, and the choices we make in the coming decades and centuries will likely determine which of the many possible futures we move toward. This is actually, in a quiet way, one of the most remarkable facts about our moment in history. We are the first generation of humans who can genuinely see the long-term risks to our species and have at least some ability to respond to them. Every generation before us faced threats they could not fully understand or prepare for. We are the first with the tools to try. With all of that in mind, let us now turn toward the deeper future, beyond the risks of the next few centuries, into the longer timescales that science can begin to sketch, even if it cannot draw them in full detail. Because here, the picture becomes genuinely extraordinary. Imagine for a moment that humanity navigates the near-term risks, that we manage our environment more carefully, buys to develop artificial intelligence that remains beneficial. Imagine, in other words, that we make it through the next few hundred years intact. What then? What does the deep future actually look like? Scientists who specialize in astrobiology and in what is sometimes called long-term futures research have begun to map out what might be possible. And the answer is simultaneously humbling and almost breathtaking in its scale. Because if humanity survives the near term, the window of time available to our species is not just long, it is almost beyond comprehension. Let us begin to explore what that might actually mean. Think about where we are right now, roughly 12,000 years since the dawn of agriculture. About 5,000 years since the first cities, less than 300 years since the Industrial Revolution. Less than 100 years since we first left the atmosphere. The pace of change in human civilization has been accelerating. Each century building on the last, each generation inheriting tools and knowledge that would have been unimaginable to their grandparents. Now, project that forward, not by decades, but by thousands of years. 10,000 years from now, if civilization continues and technology advances What might humanity look like? We cannot know the specifics, but we can consider the direction. If the past 10,000 years took us from stone tools to quantum computers, what might the next 10,000 years produce? The honest answer is, we cannot imagine it, just as a person living in 3000 BC could not have imagined the internet, or the space shuttle, or the view from the International Space Station looking down at Earth. We cannot imagine what 10,000 years of further development might bring. But here is what we can say. On the timescale of thousands of years, Earth remains a remarkably stable and habitable planet. The continents will have shifted slightly. The sea levels will have changed. The climate will have fluctuated within natural ranges. But fundamentally, Earth at 10,000 years from now will still have breathable air, liquid oceans, arable land. The sun will shine at roughly the same intensity. The moon will still pull the tides. The magnetic field will still deflect harmful radiation. In other words, if we manage the near-term risks, the planet itself will continue to support us for a very long time. And as we extend our imagination further, out to 100,000 years from now, the picture remains broadly similar. Ice ages will have come and gone. The continents will look slightly different. Volcanic activity will have reshaped some coastlines. But Earth will still be recognizably Earth, still turning, still blue and green and swirled with white clouds. From the perspective of space, still home. Now let us push even further. 1 million years into the future. 1 million years. This is a timescale so vast that it becomes difficult to hold in the mind. Consider that 1 million years ago, Homo erectus, an early human ancestor, was learning to use fire for the first time. Language as we know it did not yet exist. Agriculture was still nearly 1 million years away. In 1 million years, the world will look genuinely different. The continents will have moved. Current mountain ranges will have eroded significantly. New geological features will have formed. The climate will have cycled through many ice ages. Some species alive today will be extinct. New ones will have evolved. And if humanity still exists, if our descendants are still here in some form, they will be separated from us by a gulf of time, greater than the gulf that separates us from Homo erectus. They may not think like us. They may not organize themselves like us. They may have altered themselves through technology, through biology, through ways we cannot yet conceive. But they might still be here, still, somehow, us. And on this timescale, one of the most fascinating questions scientists explore is what humanity's relationship with this planet might look like. Because by 1 million years from now, if our civilization has continued to develop, it is plausible that our descendants would no longer be confined to Earth. The technology required to establish permanent settlements elsewhere in the solar system is not science fiction on a 1 million year timescale. It is almost certainly achievable. Mars is the most obvious candidate, a cold, thin atmosphered world that is nonetheless reachable with current rocket technology in a matter of months. Scientists have been designing Mars colonization concepts for decades, and while the engineering challenges are enormous, they are not physically impossible. Given centuries of further development, a permanent human presence on Mars seems not just possible, but likely. And beyond Mars, the moons of Jupiter and Saturn offer further possibilities. Europa, a moon of Jupiter, is believed to have a liquid ocean beneath its icy surface. Titan, a moon of Saturn, has a thick atmosphere and lakes of liquid methane. Strange worlds, but worlds nonetheless. The reason scientists find this expansion so important is not simply ambition, it is resilience. A species confined to a single planet is vulnerable to a single planet's events. A species spread across multiple worlds is far more difficult to extinguish. This is sometimes called the backup civilization argument, and it has been taken seriously by many of the world's leading scientists and thinkers. Because the logic is simple. As long as we exist only here, a sufficiently large catastrophe here could end everything. But the moment we become a multi-planetary species, our eggs are no longer in one basket. A catastrophic event on Earth, as devastating as it would be, would no longer represent the end of our story. Survivors elsewhere could endure, could eventually return, could rebuild. The transition from single planet to multi-planet species may be one of the most important thresholds in our entire history, and on the timescales we are discussing tonight. That threshold is not impossibly far ahead. It is, in fact, potentially within the reach of the next few centuries. But let us return to Earth itself, because even setting aside the question of expansion beyond our planet, Earth's own timeline of habitability is genuinely remarkable. Scientists who study planetary habitability have spent decades trying to understand exactly how long our planet can continue to support complex life. And the answer depends on several interacting factors. The most fundamental of these is the Sun. Our star, like all stars, is not static. It is slowly, steadily changing. Right now, the Sun burns hydrogen in its core, fusing it into helium and releasing enormous amounts of energy as light and heat. This process has been running for about 4.5 billion years, and it will continue for approximately another 5 billion years. So the Sun itself is nowhere near the end of its life, but here is the subtlety. As the Sun ages, even while it is still in this stable phase of its life, it is slowly, very gradually, getting brighter. The Sun today is roughly 30% brighter than it was when Earth first formed, and it will continue to brighten over billions of years. That slow brightening is the most fundamental long-term threat to life on Earth. Not an asteroid. Not an asteroid. Not a supervolcano. Not any human-created risk, but simply the slow, inevitable evolution of our own star. As the Sun grows brighter over the next billion years, the temperature on Earth's surface will gradually rise. The oceans will slowly begin to evaporate more quickly, water vapor, entering the atmosphere in greater quantities, will enhance the greenhouse effect, creating a feedback loop that gradually accelerates the warming. Scientists estimate that within roughly 1 billion years from now, conditions on Earth's surface may become too hot and dry for most complex life as we know it today. The oceans could largely evaporate. The atmosphere could shift dramatically. The lush green, blue-white world we know could become something far more arid, something approaching, in some distant echo, the surface of Venus. 1 billion years. That is the rough scientific estimate for how long complex life on Earth, in anything resembling its current form, may be able to survive. 1 billion years. Let that settle for a moment. 1 billion years is so vast that it almost loses meaning as a number. Let us try to feel its scale. The dinosaurs went extinct 66 million years ago. 1 billion years is 15 times longer than that. The Cambrian explosion, when complex animal life first appeared, was 540 million years ago. That question is this: how long might humanity actually have left on this planet? Not in a frightening way, not as a warning, but as a genuine scientific exploration of time, of scale, of what the future might actually look like across thousands, millions, and even billions of years. Because the answer is far more surprising than most people ever expect. Let us go back to where it all began. 4.5 billion years ago, there was no Earth. There was no sun. There was only a vast, slowly rotating cloud of gas and dust, drifting through a region of the galaxy that had no name, because there was no one to name it. And then, slowly, over millions of years, gravity began to pull that cloud inward. Particles attracted other particles. Dust gathered dust. Gas collapsed upon itself. And at the center of all that slow, quiet compression, a star ignited. There is another dimension to this question that scientists explore with particular care. Not just how long Earth can support life, but whether humanity itself, in some form, could outlast the habitability of this particular planet. This brings us to one of the most extraordinary concepts in long-term futures thinking: the idea of an interstellar civilization. Our nearest neighboring star system, Alpha Centauri, is roughly 4.2 light-years away. At the speed of our fastest current spacecraft, it would take approximately 70,000 years to reach. On a biological timescale, that seems impossibly far. But consider the context. Our civilization is roughly 12,000 years old. If it continues for another 60,000 years, we would have the full 70,000 years required to reach the nearest stars. Using existing propulsion principles, let alone anything more advanced, and scientists have already proposed theoretical spacecraft designs that could reach Alpha Centauri in decades rather than millennia. Laser-propelled light sails, nuclear pulse drives, technologies that are physically possible, even if they require engineering far beyond our current capability. The point is not that interstellar travel is imminent. It is not. The point is that on deep timescales, the barriers that seem absolute today may not be absolute at all. They may be engineering challenges, problems of resources and time and ingenuity, and those are the kinds of problems that humanity has a long history of eventually solving. Think about how flight itself seemed impossible until it was not. Think about how the idea of standing on the moon was once considered pure fantasy. The history of human achievement is largely a history of deciding that something impossible was merely difficult, and then doing it anyway. Whether humanity will ever actually reach the stars is a question that cannot be answered tonight, or perhaps in any of our lifetimes, but the fact that it is physically possible, that the laws of nature do not forbid it, is itself a remarkable thing to sit with, because it means the ultimate ceiling on our story may be set not by physics, but by choices, by will, by the kind of species we decide to be. Let us come back now from those vast distances and settle into a quieter reflection, because all of this The risks and the timelines and the billions of years and the neighboring stars can feel abstract, can feel like numbers rather than meaning. So let me try to offer something more grounded, something that connects all of this to the moment you are in right now. You exist at an extraordinary point in time, not because of technology, not because of progress, but because of position. You are alive at the very beginning of the human story in 10,000 years, or 100,000 years, or 1,000,000 years. If descendants of ours still exist, they will look back at this era the way we look back at the earliest cave paintings, as the beginning, as the first tentative marks of something that would eventually become something vast. And there is something quietly moving about that, about being here at the start, when everything is still so new, when the questions are still so large, when the future stretches ahead in ways that no one can fully see. What they call the critical period, the window of time, roughly the next few hundred years, in which the choices our civilization makes will likely determine which of many possible futures we move toward. This period is critical, not because the risks are certain to end us, but because the decisions made now will compound across centuries. The direction we set in this era will shape where our descendants find themselves 1,000 years from now. And this is, when you sit with it, a profound kind of responsibility. We are not just living our lives, we are setting trajectories. The carbon we emit, the species we protect or fail to protect, the treaties we sign, the technologies we develop carefully or carelessly, the institutions we build or allow to decay, all of these are not just decisions for today. They are messages sent forward in time, instructions left for people who will not remember writing them, conditions inherited by children who did not choose them. That is a heavy thought, and also a clarifying one. There is a concept in long-term thinking, sometimes called deep time awareness. It is the practice of truly, genuinely feeling the scale of time that surrounds us, not just knowing intellectually that Earth is 4.5 billion years old, but actually trying to inhabit that knowledge, to feel it. Because when you do, something shifts. The anxieties of the immediate present do not disappear, but they become contextualized. They take their place within something much larger, and from that larger perspective, things that feel urgent and irreversible can begin to feel like one chapter in a very long story. This is not a reason for passivity. It is not an argument that nothing matters because everything is temporary. Quite the opposite. The fact that we exist at all, in this specific, improbable, brief window of cosmic time, makes this moment all the more worth caring about, all the more worth taking seriously, all the more worth trying to get right. Deep time awareness is not numbing. When done well, it is clarifying. It reminds us what actually matters and what does not. Let us now consider the very far end of Earth's story, not in billions of years, but in the final chapter of the Sun itself. Approximately 5 billion years from now, the Sun will have exhausted the hydrogen in its core. At that point, it will begin to fuse hydrogen in a shell around its core instead. This will cause the outer layers of the Sun to expand enormously. The Sun will swell into what astronomers call a red giant, growing hundreds of times its current size, so large that it may engulf the inner planets, Mercury, Venus, and possibly Earth itself. By this point, Earth's surface will long since have become uninhabitable. The oceans will be gone. The atmosphere will have been stripped away. The planet, if it still exists, will be a silent, scorched, airless rock, drifting in the expanding outer layers of a dying star. There is something quietly poetic about that image, the same star that spent billions of years nurturing life on this world. Eventually, at the end of its own life, reclaiming the planet it gave birth to. A slow, cosmic completion. But that is 5 billion years away. 5 billion years. More than 3 times the entire current age of our civilization would need to pass, 1,000,000 times over, before we reached that moment. In every meaningful sense, it is not something we need to worry about tonight, or in any foreseeable future. It belongs to an era so distant that anything we might say about human civilization at that point would be pure imagination. What we can say is that if descendants of ours still exist at that point, they would be so different from us, so separated by billions of years of development, that the word human would likely carry no useful meaning anymore. They would be something entirely other, something we cannot name, something we cannot imagine. And perhaps that is one of the most quietly beautiful aspects of this entire question. The future is not just unknown, it is unimaginable. It stretches beyond the reach of any story we could tell about it tonight, and yet it is continuous with this moment, with this breath, with this quiet room. Let us take a moment now to gather what we have explored. We began 4.5 billion years ago in a cloud of gas and dust, slowly collapsing under gravity. We watched a planet form. We watched life appear, quietly, in ancient oceans. 3.8 billion years ago, we watched complexity emerge. We watched the first animals appear. Then, in the very last fraction of Earth's story, we appeared. Modern humans. Extraordinarily new, remarkably capable, and carrying, already, the seeds of something that might outlast everything that came before us. We explored the risks that could cut our story short. The asteroids we can now track and deflect, the volcanic events that have tested us before and found us resilient, the climate shifts that shaped our ancestors, and the newer risks, the ones we created ourselves, which are harder in some ways because they require us to govern ourselves wisely, something we are not always perfectly good at, but something we are, slowly, getting better at. We looked forward into the deep future, into thousands and millions and hundreds of millions of years, into a window of time so vast that any story told about it must be told in the language of imagination rather than certainty. And we found something surprising, not a timeline rushing toward an end, but a timeline still mostly ahead of us. Earth has roughly 1 billion years of habitability left for complex life, perhaps more, if we develop the technology to manage the slow brightening of the sun. 1 billion years. In a species' history measured in hundreds of thousands, 1 billion years represents a future so large, it has no comparison we can easily reach for. It is more time than the entire history of complex animal life on Earth. It is more time than almost any human concept can meaningfully hold. And within that billion years, our descendants might do things and become things that we cannot begin to imagine. The 3 billion-year-old ocean could not have imagined you. There's one more thing worth sitting with tonight. Before we begin to drift toward the end of this exploration, the question we started with, how long might humanity have left on Earth, carries a subtle assumption that our story is one of limited time, a countdown, a finite window. But when you look at the science, that framing does not quite fit. It is not that humanity has a fixed amount of time remaining, like a sand timer running out. It is more that we are at the beginning of a journey, whose length and direction depend enormously on the choices we make. The future is not fixed. It is not determined. It is, in a very real sense, being written right now. By the decisions of governments and scientists and engineers and farmers and parents and teachers. By the slow accumulation of choices made by billions of people across decades and centuries. The question is not just how long we have left. The question is, what do we do with the time we have? And that is a question every generation must answer for itself. As you lie here tonight, perhaps already beginning to feel the edges of sleep, I want you to carry this with you, not as a weight, but as a quiet companion. You are part of something enormously old and potentially enormously long. The atoms in your body were forged inside ancient stars, stars that exploded billions of years before the Earth existed, scattering their material into the cosmos, where it eventually found its way into a cloud of gas and dust. That collapsed into a solar system, that formed a planet, that cooled and grew oceans, and gave rise to life, and eventually to you. You are made of star material. You are the universe experiencing itself. And the question of how long humanity lasts on this planet is in some small way a question about whether the universe continues to have the opportunity to look at itself through eyes like yours, through minds like yours, through the particular, improbable, precious kind of awareness that we call being human. The scientists who dedicate their lives to these questions often describe experiencing a particular kind of feeling when they really inhabit the scale of what they study. It is not fear. It is not despair. It is something closer to awe, a quiet, overwhelming, almost physical sense of how vast the story is, and how small and brief, and yet how remarkable our part in it is. The paleontologist who holds a 300-million-year-old fossil in their hands and feels the weight of deep time pressing through that stone. The astronomer who trains a telescope on a galaxy whose light left before Earth was formed and realizes they are looking at something that happened before the planet they are standing on even existed. These moments do not make the scientists feel insignificant. They make them feel connected. Part of something continuous. Part of something that began long before them and will continue long after. That feeling is available to any of us who take the time to sit quietly with these questions, as you are doing tonight. Sleep is coming now. You can feel it. The thoughts slowing. The room becoming quieter in that particular way it does when the day has finally let go. And I want to leave you with an image. Imagine Earth from space, the way the astronauts see it. A small, blue, impossibly vivid sphere, suspended in an ocean of darkness, surrounded by stars, each one older and further than the mind easily reaches. And on that small blue sphere, clinging to its surface, billions of people, billions of lives, billions of small decisions and quiet moments and ordinary days, adding up to something that has never existed before in the known universe. A species that can think about its own future. A species that can ask, how long? And listen, and wonder. That is what you are. That is what we all are. Something new under an ancient sun. Something brief in a vast story. Something that matters precisely because it knows that it matters. The question of how long humanity might have left has no single clean answer, because it is not really a question about time. It is a question about what we do with time, and the answer to that is still being written. By people who will never know their names are part of the answer. By decisions that seem small in the moment, but ripple forward across generations. By the scientist working late in a lab, studying climate patterns or vaccine design or asteroid trajectories. By the engineer designing better systems. By the teacher who makes a child curious about how the world works. By the parent who chooses carefully. By the person who decides that the future matters, that it is worth caring about, that the story is worth continuing. Science tells us that if we are careful, the story could continue for an almost unimaginable length of time. The universe is ancient and patient, and it does not rush us. The time is there. What we make of it is up to us, and yet there is something we have not yet fully explored tonight. Something that sits quietly at the edge of all these vast timescales. A question that scientists rarely ask out loud, but which underlies almost everything we have discussed. What does it actually mean for a civilization to survive? Because survival is not just about avoiding extinction. It is about continuity, about something being carried forward. Think about what has already been lost. Languages that no living person speaks. Entire systems of knowledge developed over centuries, erased by war or disaster or simple neglect. Musical traditions. Agricultural techniques. Ways of understanding the natural world. That took thousands of years to accumulate and were gone within a generation. The Library of Alexandria. The oral traditions of displaced peoples. The scientific knowledge of civilizations that simply faded. Every one of these losses represents a kind of small extinction, not of people, but of understanding. And scientists who think seriously about the long-term future of humanity often argue that the preservation of knowledge is just as important as the preservation of life, because a humanity that survives physically but loses the accumulated understanding of how to maintain complex civilization is a humanity that must begin again, and beginning again is expensive. It costs centuries, sometimes millennia. The transition from the fall of the Western Roman Empire to the technological sophistication of the Renaissance took roughly 1,000 years, 1,000 years of slower development, of knowledge fragmenting and reassembling, of hard-won understanding having to be rediscovered. The lesson scientists draw from this is not pessimism. It is that knowledge itself is one of the most precious and fragile things our species produces, and protecting it, passing it forward intact, may be one of the most important things any generation can do. There is a project that has existed quietly for decades that captures this idea beautifully. It is called the Long Now Foundation, and its central mission is to encourage long-term thinking, to help humanity develop what its founders call a 10,000-year clock of the mind, a way of orienting our decisions, not around the next quarter, or the next election cycle, or even the next generation, but around the next 10,000 years. As part of this project, they are building an actual clock, a mechanical clock designed to keep accurate time for 10,000 years. It is being constructed inside a mountain in West Texas, powered by thermal cycles, the natural expansion and contraction of metal, as the mountain heats during the day and cools at night. It will tick once a year. Its century hand will move once every 100 years, and a cuckoo will emerge once every millennium. There is something deeply moving about this. The idea that someone would build something, not for any person alive today to see completed in their fullness, but for people 10,000 years from now, people whose language we cannot predict, whose civilization we cannot imagine. But who will? The builders hope stand inside that mountain and hear a mechanism ticking. That was set in motion by ancestors they will never know, by people who cared enough about the future to build something for it. That is a kind of love, a love extended across time, across the vast anonymous gulf of centuries, and it suggests something important, that the question of how long humanity lasts is not just a scientific question, it is a moral one. It asks what we owe to the future, what we are willing to build, that we will never see finished, what we are willing to protect. For people who do not yet exist, scientists who study civilizational risk often point to something they call the Great Filter. It is a concept that emerges from a simple and quietly unsettling observation. The universe is approximately 13.8 billion years old. It contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars, and around many of those stars are planets. Some of those planets, based on everything we know about chemistry and physics and biology, should be capable of supporting life, and yet, we have found no evidence of any other civilization, no signals, no structures, no signs of any other species that has done what we have done, looked outward, reached toward the stars, left a mark on the cosmos. The silence is, when you really sit with it, remarkable. And the Great Filter concept asks a difficult question. Why? Why is the universe so quiet? There are two broad categories of answer. The first is that the filter is behind us, that the steps required to produce intelligent technological life are so extraordinarily unlikely that we may genuinely be the only civilization of our kind in the observable universe, or one of an almost vanishingly small number. In this version, the silence is explained by rarity. We are simply improbably rare, and the filter we have already passed through, the emergence of complex life, of consciousness, of technology, was the hard part. The second possibility is that the filter is ahead of us, that something about the transition from a young technological civilization to a mature, stable one is genuinely difficult, genuinely dangerous, and most do not make it. This is the version that asks the harder question: are we the exception, or are we still approaching the filter? The honest answer is that we do not know. We do not know whether we are rare. We do not know whether the filter is behind us or ahead. We do not even know for certain that the silence is real. Perhaps other civilizations exist, and we simply have not listened in the right way, or have not listened long enough, or are separated by distances so vast that no signal sent by either side has had time to arrive. The universe is under no obligation to make itself easy to read. But what scientists find interesting about the Great Filter concept is not the fear it might seem to generate. It is the responsibility it implies. If we are rare, then we are precious, not in a sentimental way, but in a genuinely cosmic sense. The emergence of consciousness, of curiosity, of a species that builds telescopes and writes poetry and wonders about its own origins may be one of the rarest things in the universe. And if that is true, then allowing it to end through carelessness or short-sightedness or simple failure to cooperate would represent a loss of almost incomprehensible magnitude, not just for us, but for the universe itself, which would, in losing us, lose one of the very few mirrors it has in which to see itself. There is something in that thought that changes the weight of the question we are exploring tonight. It is no longer just about our survival. It is about what our survival might mean in a cosmos that may be, for all its unimaginable scale, quieter and lonelier than it appears. We might be the ones keeping a particular kind of light alive, the light of awareness, of understanding, of a mind turned outward toward the dark and finding it fascinating. Let us come back to Earth for a moment, to something more immediate, more grounded, because all of these vast ideas, the Great Filter, the long now, the billion-year habitability window, can begin to feel abstract, can begin to feel like they belong to someone else's story, and they do not. They belong to this story, to the species lying awake on this particular planet, on this particular night. So let us talk about something closer, something that scientists consider one of the most hopeful signs in the entire landscape of long-term human futures: the demographic transition. For most of human history, population growth was driven by one simple dynamic: high birth rates and high death rates, more or less balancing each other out. Life was short, childhood mortality was devastating, and families had many children, because many of those children would not survive to adulthood. But as living standards improved, as medicine advanced and food security increased, something unexpected happened. Birth rates fell, not because anyone told people to have fewer children, but because when children reliably survive, when education is available, when women have economic agency and opportunity, families naturally choose to have fewer children and to invest more deeply in each one. This pattern has now repeated in country after country, across every culture and continent where development has taken hold, and the implication for the long-term future of humanity is significant, because it suggests that human population may not grow indefinitely. Current projections suggest global population may peak somewhere between 9 and 11 billion people later this century, and then slowly begin to stabilize or even decline. A humanity that stabilizes its population places fundamentally different pressures on the planet than one that grows without limit. And this connects to something even deeper, something that scientists who study long-term civilizational health find genuinely encouraging. The trend toward what they call institutional maturity. For most of human history, large-scale cooperation was extraordinarily difficult. Different groups competed for resources. Borders were defended violently. The idea of nations voluntarily surrendering aspects of their sovereignty for the benefit of shared global goals would have seemed absurd to most rulers throughout history. And yet, that is exactly what has slowly, imperfectly, haltingly begun to happen. The creation of the United Nations after World War II, the development of international scientific cooperation, that produced the mapping of the human genome, the detection of gravitational waves, the imaging of a black hole for the first time, the international agreements around ozone depletion, which successfully reversed the damage to the ozone layer. In one of the quietest and most underreported environmental success stories of the modern era, these are not perfect institutions. They are slow and frustrating and often inadequate. But they represent something genuinely new in human history: the embryonic infrastructure of global cooperation. And on the timescale of centuries, the difference between a humanity that has learned to cooperate globally and one that has not may be the difference between a species that navigates the coming challenges and one that does not. The institutions we are building now, imperfect as they are the foundations of something that may not reach its full potential. For hundreds of years, we may not live to see them work as intended, but we are the generation laying the groundwork. And that is not a small thing. That is perhaps one of the most important things happening on this planet right now. Quietly, without fanfare, in the background of everything else, there is a thought experiment that scientists and philosophers sometimes use when trying to communicate the stakes of long-term human survival. It goes like this. Imagine a village of 1,000 people. Now imagine that village faces a threat. A flood is coming, and the villagers must decide whether to spend resources building a levee that will protect the village, not for them, but for the people who will live there in 500 years. People none of them will ever meet. People who will never know their names. The question is, do they build it? In theory, most people say yes. Of course you protect the future. Of course you build the levee. But in practice, across human history, this kind of long-term investment has been extraordinarily difficult to sustain because the benefits are invisible. They accrue to people who do not yet exist, and the costs are immediate. They fall on people who are alive right now. And yet, the civilization we inherited tonight was built entirely by people who made exactly that choice. People who planted trees whose shade they would never sit under, who built cathedrals that took 300 years to complete, who developed scientific knowledge they knew would not be useful within their own lifetimes. Every piece of infrastructure that makes modern life possible was built by someone who was investing in a future they would not personally live to see. We are the beneficiaries of 10,000 years, of people building levees, of people choosing the future over the immediate. And the question that quietly underlies everything we have explored tonight is whether we will do the same. Whether we will be the generation that keeps building, that keeps choosing, that keeps the story going. There is one more dimension of the deep future that deserves its own quiet moment of attention. The question of what humanity itself might become Because when we talk about humanity surviving for millions of years, we are making an assumption that deserves examination. We are assuming that the beings who exist millions of years from now will still be recognizably human, and that assumption may not hold. Evolution does not stop. It has never stopped. Every species on Earth is a temporary form, a snapshot of a lineage in motion. The humans of today are not the final version of anything. We are a stage, a point along a continuum that began billions of years ago and has no reason to end with us. On timescales of millions of years, natural selection alone would produce descendants noticeably different from us, different enough that if we could see them, we might not immediately recognize them as kin. But natural evolution is slow, and we are no longer subject only to natural evolution. We are the first species in the history of this planet that can deliberately modify its own biology. Gene editing technologies already exist that allow targeted changes to the human genome, crude and early by any future standard, but pointing in a direction that is difficult to look away from. Within centuries, the ability to alter human biology deliberately may be as routine as the ability to alter software. And within millennia, the definition of what it means to be human may have shifted so profoundly that the word itself becomes inadequate, not a loss, but a transformation. The caterpillar does not mourn the butterfly. It simply becomes it, and whatever our descendants become, if they carry forward curiosity and care and the capacity to wonder, then something essential will have survived. Scientists who think seriously about these questions often arrive at a concept called the adjacent possible. It is the idea that at any given moment, the next step forward is constrained by what currently exists. You cannot build a smartphone without first having microprocessors. You cannot have microprocessors without first having transistors. You cannot have transistors. The old shoe. Every door that opens reveals a corridor with new doors, and the corridor of the adjacent possible for humanity right now is wider than it has ever been. The tools we have developed in the last 100 years have opened more new doors than in all of previous human history combined. Quantum computing, genetic engineering, material science operating at the atomic scale, artificial intelligence capable of accelerating scientific discovery, telescopes that can study the atmospheres of planets orbiting other stars. Each of these is not just a technology. Each is a key to corridors that lead to more corridors, and the pace at which we are opening those doors is still accelerating. Now, this does not mean everything will be fine. New doors can lead to dangerous rooms as well as beautiful ones. The adjacent possible includes threats as well as solutions. But it also means that the tools available to future generations for managing the risks we have discussed tonight will be tools we cannot currently imagine. Just as the people of 1900 could not have imagined using satellite data to track an approaching hurricane, or sequencing a virus's genome within hours of its discovery, the solutions of the future are being built right now in labs and universities and garages by people who do not yet know what they are building toward. And this brings us to perhaps the thing that sits underneath all the timescales and risks and possibilities, like a bedrock. Every generation of humans, in every era of our history, has faced a version of this question. Will we make it? The early humans huddled through the Toba winter, a supervolcanic catastrophe that may have reduced our entire species to a few thousand survivors. Did they believe they would make it? We cannot know, but they did. The civilizations that fell to plague and famine and invasion, the generations that lived through the chaos of collapsing empires, the people who survived the 20th century, with its 2 world wars and its nuclear standoff, and its almost incomprehensible catalog of suffering. Every one of those generations had reason to doubt, had reason to wonder whether the story would continue, and in every case, it did. Not because of certainty, not because someone guaranteed the outcome, but because enough people, in enough places, kept going, kept building, kept choosing tomorrow over despair. There is a kind of quiet heroism in that, a heroism that does not make the history books, that does not get monuments or commemorations. In many ways, the most important thing our species has ever done, the simple, stubborn, daily choice to continue. And tonight, on this particular night, in this particular quiet room, you are part of that same continuity. You are the latest in an unbroken line, stretching back 300,000 years, through every hardship, through every near ending, through every moment when the story could have stopped and did not. You are here because they kept going, and whatever comes next begins with the same simple act, waking up tomorrow and continuing. The ocean is still moving tonight. Somewhere on the other side of the world, a wave is forming in deep water, building slowly, traveling thousands of miles toward a shore it has never touched. It does not know where it is going. It simply moves. Because that is what water does when energy passes through it. And in some ways, that is what we are. We are the medium through which something larger moves, something that began in the chemistry of an ancient ocean and has been building ever since. Through every form it has taken, every organism, every species, every civilization, every quiet mind lying awake at night, wondering how long. We are not separate from that process. We are it. The universe organizing itself into something more complex, more aware, more capable of understanding its own nature. And the question of how long humanity lasts is, in the deepest sense, a question about how long that process continues. How long the universe keeps finding new ways to know itself, to feel itself, to look at its own reflection in the still water of a conscious mind. Scientists can give us timescales. They can map the risks and sketch the possibilities. They can tell us about billion-year windows and solar evolution and the slow drift of continents. But the deepest answer to the question is not in any of those numbers. It is in the simple fact that we are still asking. That after everything, after every hardship and every near miss and every dark chapter, we are still here, still curious, still reaching, still lying awake at night, wondering about things that are larger than ourselves. That is not nothing. That is everything. There is a word in Welsh that has no direct translation in English. The word is hiraeth. It describes a kind of longing, but not for something you have lost in your own life. It is a longing for something you cannot quite name, a homesickness for a place you have never been, a grief for something that exists just beyond the edges of memory. Philosophers and poets have tried to capture it in many languages. That particular ache of being a temporary creature in a world that will continue without you, of loving something, knowing you will not always be there to love it. I think about that feeling sometimes in the context of everything we have explored tonight, because there is something in the human relationship with time that carries exactly that quality. We love this world. We love the oceans and the mountains and the particular quality of light. On a late afternoon in autumn, we love the people we share our brief years with. We love the ideas we discover, the questions we cannot stop asking. And somewhere underneath all of that love is the quiet awareness that it is temporary, that we are temporary, that even the planet itself, on the longest timescales, is temporary, and yet the love does not diminish because of that. If anything, it intensifies. The temporary nature of things is part of what makes them precious. The cherry blossom is not less beautiful because it falls. The sunset is not less worth watching because it ends. And this life, this strange, brief, improbable, extraordinarily specific life, is not less worth living because it has limits. Perhaps it is worth living precisely because it does. We are nearly at the end of tonight's journey, and I want to take one final moment before sleep comes to gather everything we have explored into something you can carry with you, not as a list, not as a set of facts, but as a feeling, because that is what this kind of knowledge is really for, not to fill a notebook, but to change, very slightly, the way you see. You live on a planet that is 4.5 billion years old. You are part of a species that has existed for 300,000 of those years. Your civilization is roughly 12,000 years old, and the window of time still available to life on this planet extends for perhaps 1 billion years more. You exist at the very beginning of something that has barely started, something that, if we are careful and wise and cooperative enough, could become more extraordinary than anything that has come before. The risks are real. We have not pretended otherwise tonight. But they are not destiny. They are challenges. And challenges, as the entire history of our species demonstrates, are things we have a remarkable capacity to meet. Not perfectly, not without cost, but genuinely, with creativity and stubbornness and the particular human refusal to simply accept that something cannot be done. You are part of that story, not a passive observer, but an active thread in the fabric of something that stretches back to the beginning of life and forward, further than any mind can see. That is who you are. That is where you come from. And that is, in the quietest and most grounded sense, reason enough to rest easy tonight. You are part of something that has survived everything and intends to keep going. And so, we come gently to the end, not with answers. The biggest questions rarely end with answers. They end with a different kind of quiet, a quieter curiosity, a more settled sense of wonder. You came to this tonight asking, how long might humanity have left? And the science says, more than you thought. Far more than the anxious headlines suggest. Far more than the noise of the immediate present implies. If we choose well, if we build carefully, if we extend our thinking beyond the next year and the next decade, into the next century and the next millennium, the future available to our species is almost beyond imagining. 1 billion years of planetary habitability, potentially millions of years of expansion beyond this world. And somewhere at the far edge of all of that, something we cannot name. Something that will have grown from this moment. The way an oak grows from an acorn, carrying something essential forward, into forms we cannot predict. That is the story you are part of. That is the scale of the thing you belong to. And tonight, you have sat with that. You have let it breathe. You have given it the quiet attention it deserves. And now, it is time to rest. Let the vast timescales recede. Let the billion years fold back into the dark. Let the questions rest where questions rest, at the edges of a sleeping mind. The universe will still be here tomorrow, still ancient, still patient, still turning, and so will you. Good night. If you find yourself lingering here, in the space between wakefulness and rest, know that there is no rush. Stay here and allow the calm to carry you forward, and if your curiosity is still softly humming, another world of quiet knowledge is waiting for you on your screen right now. Let the next story carry you a little further into the calm, until the words eventually turn into dreams.